classwork, time series, material, handouts, open. Time series. A time series is a collection of data recorded over a period of time. Therefore, mathematically, this is a record of time and a record of data together. Statistically, this is a pair of two samples matched data. For each case, we record time and value. Maybe weekly, maybe monthly, maybe quarterly, yearly, anything, periodically. In the theory of time series, statisticians studied 4 parts: secular trend, long-term direction of the business, straight line concept, cyclical variation, rise and fall of some years, rise and fall of business, seasonal variation, rise and fall pattern in 1 year. The rest is irregular variation. We will study secular trend T and seasonal variation together, which can be used to estimate the future value. We won't study C and I. Secular trend: to study the long-term direction of business, we will use least squares method, simple linear regression, where the independent variable is time t. We write t for time. In computation, we measure time in a suitable unit. There are many units, many standard units of time: seconds, minutes, hours, week, day, week, month, year, and so on. But we will use suitable unit for the business concerned. After that, seasonal index S. Seasonal index is rise and fall, extent of rise and fall by season in 1 year. The technique is the classical technique. Seasonal index is value ratio to average percentage form. Okay. Ratio to moving average method, this is listed here. 1, 2, 3, 4, 5. And for knowledge, you know that there are 2 models of time series used in predicting future values. Multiplicative model, the product of 4 components: trends, cyclical, time series, and irregular. Another is additive model, the sum. This is for knowledge. We will use this problem 25 as example. You can read it. Okay, the first question is construct the trend line. So least square line, time is the independent variable because we want to estimate value using time. Therefore, time is independent, value is y dependent. And here time is recorded in year and quarter. Quarter means 3 months. So to use simple linear regression with calculator, you have to set in simple linear regression mode. After that, enter time value in pairs, we have to choose one suitable unit to measure time. Here we don't have mathematical unit yet. We record only 2010, quarter 1, 2010, quarter 2, and so on. Okay, let's start from beginning, 0. After 3 months, we record 2. After the next 3 months export is 3. After that, the next 3 months export is 6. So, if we write 1 unit for 3 months, it is suitable. Small numbers and suitable units, because we record only once 3 months. So, at the end of the first unit of time, at the end of 1 unit, after 1 unit of time has passed, we export 2. So, time 1, value 2. At the second unit of time, the export is 3. So, time 2, unit 3. After that, time unit 3, number 3, value 6. Time unit 4, value 4. After that, after another 3 months, fifth 3 months, 2011, first quarter, time 5, value 2. After that, 2011, second quarter, time 7th unit, export 2, 7, 2, and so on. After that, 7, 7. After that, 8, 5. After that, 9, 2. After that, 10, 4. After that, 11, 8, 12, 6, 13, 1, 14, 3, 15, 8, 16, 6. Enter. After entering, press A. You will see 2.95. Press B. You will get 0.1529 to the nearest fourth decimal. Therefore, you get the answer to 25.1. Y hat is equal to 2.95 plus 0.1529t. The purpose of constructing the regression line is estimating. 25.2. Using the trend line, estimate the value of grain to export in quarter 1, 2014. So in the equation 25.1, what t value shall we enter? So let's check the table. 2013 quarter 4 is time value 16 units. So after that, 2014 quarter 1 is time unit 17. So enter 17 in T and compute Y hat estimated export. You will get 5.55. So 5.55 million tons. Okay, next. About seasonal indices. Check this prediction. 5.55 million tons. If you see back the table, in quarter 1, export amounts are only 2 millions, 2 millions, 2 millions, 1 million. After that, by regression line estimates, the next year quarter 1 export will be 5.55 million tons. This is normally impossible. This is agricultural grade export. What happens? Then you plot the scatter points and check. In this diagram, you will see for every year, quarter 1 value is lowest, quarter 2 a little up, quarter 3 highest, quarter 4 drops down and stay a little more than quarter 2 value. So this pattern, quarter 1, quarter 2, quarter 3, and fall down. quarter 1, 2, 3, rising up, quarter 4, fall down. So every year this pattern you see, the same pattern. Every year the same pattern, similar pattern. Therefore, in this time series, seasonal pattern exists. And if you draw the regression line amid the scatter points, you will see this slowly rising straight line with small positive slope. That means the business is going up slowly. And this least square line is the best fitting line to the scatter points. Therefore, this line runs through the middle of the points, we can say. Therefore, if you use this straight line to estimate, let's check. Quarter 1 is always below the straight line. So quarter estimate value is on the line. Quarter 1 actual value is always below the line. So we check. Quarter 2 is close to the line. Quarter 3 usually above the line. Quarter 4 well above the line. Quarter 3 well above the line. Therefore, the estimated value will be quite far from actual values except quarter 2. So therefore, we cannot use 5.55 million ton estimate for quarter 1. This will not be realistic. I discussed this in 25.3. But this trend estimate is useful. Trend estimate gives 5.55 million tons, but according to the seasonal variation, seasonal pattern, the actual value will be less than 5.55. But how much less? If we know how much less, we can change to that value. How much less or how much more than the line is called seasonal index. Okay, less than the estimated value, but how much less? Yeah, we try to measure this extent. So in statistics, the classical measurement method is called seasonal index. The formula is simple. Here, seasonal index is ratio to average. Yeah, actually ratio of each seasonal value to average value for each season in a year. This is the meaning. Okay, basic idea is very simple. For instance, the fourth suppose we know four season values. First season value 60, second 80, third 40, fourth 20 suppose. Then what is their mean? Their mean is their sum 200 divided by 450. 50. So the first season value 60 is how much more than average value? 60 divided by 50. This is 1.2. In percentage form, 120%. That means season 1 value is usually 20% more than average value. Yeah, we interpret like this. Season 2, 80 ratio to average 50, 1 by 6, percentage form 160%. That means if the average value is 100, season 2 value will be 160. Now we know how much more or less. Season 1 value 20% more, season 2 value 60% of average more, season 3 value 80% only, 20% less, and season 4 value 20 over 550.4 percentage from 40. So season 4 is only 40% of average value. Now we know how much more or how much less for each season. This is the idea. Okay, this is so for usually we have many data on season time series. Then we will make use of all of them. So in detail, How shall we do? You can learn further. Now this table shows how to compute seasonal index. Note the columns. Column 1 year, quarter, and column 3 Y. You have to display the values of Y in this column vertically. The first step is to compute 4-quarter moving average. 4 successive quarters form 1 year. So in this year, you find average quarterly value Y. So first 2 plus 3 plus 6 plus 4. Then divide by 4. Average 3.75. You choose the middle one. If you see the position, you know mean of which seasons is this. 2 above, 2 below. Okay. The next 4 successive values 3 plus 6 plus 4 plus 2. Then you divide by 2. You divide by 4. Quarterly average 3.75, right in the middle of these 4 seasons. The next one 6 plus 4 plus 2 plus 2. Divide by 2. Average 3.5 in the middle. So on. You go this way. After that, you can compare each value by the corresponding averages, but the times are not quite the same. For instance, so we will not use the extreme values, the first two values 2 and 3, and the last values 8 and 6. Yeah, we will discard them because we have a lot of data. They are only extreme values. We cannot use this. This is the classic method. Okay, for instance, quarter 3 2010, quarter 3 value 6, ratio to average 3.75, the same, so no problem. Quarter 4 average, quarter 4 value 4, compared to which average? 3.75 or 3.5. Both 3.75 and 3.5 are equally entitled for 4. So, by usual statistical technique, because we have two choices, we will use their average. This way, in this way, the necessity of one more column emerged. Centered moving average for time adjustment. So let's fill this column first. First, what is the average of 3.75 and 3.75? Clearly, 3.75 right in the middle. Now this has the same time with 6. Okay, the next two 4-quarter moving averages 3.75 and 3.5. 3.75 plus 3.5 is equal to 7.25. Divided by 2 is equal to 3.625, right in the middle. The next one, what is the average of 3.5 and 3.75? 3.625, record in the middle. What is the average of 3.75 and 4? 3.875, right in the middle. So on. You fill CMA column, centered moving average. After that, you can find the ratios. For instance, we don't use quarter 1, quarter 2, the first two values. We will start with 6. Quarter 3 value 6 divided by ratio to average 3.75 multiply with 100 percentage form. This is 160 quarter 3 index, therefore right in the third column. 2010 quarter 4 seasonal value 4, average value 3.625, 4 divided by 3.625 multiply by 100. This is season 4 index 110.34. We will cut here 2 decimals. The next one 2011 Y value 2, average value 3.625, 2 divided by 3.625 multiply by 100. This is quarter 1 index 55 by 17, and so on. You compute all possible indexes, you get 3 each for each of the 4 seasons. Actually, we want only one index for one season. Therefore, for each season, we will find the average of these 3. 55.17 plus 43.24 plus 23.53 is equal to, then you get the sum total, then divide by 3 equal to, right here, 40.65 and so on. Okay, season 2 average seasonal index 51.61 plus 84.21 plus 68.57 is equal to, then divide by 3 is equal to 68.13 and so on. If you compute the mean of season 3 indexes, you get 169.32, season 4 114.09. So actually this is done. Technically this is complete, but because this is hand computation, in the past, before the time of computers, statisticians devised final correction method, correction to computational errors, because we round off each value in the process of computation everywhere. So these round off errors sum up, and the actual value may be quite different. Therefore, check. At 4 seasonal value indexes 40.65, 68.13, 169.32, 114.09. What do you get? We get 392.19. This is not equal to 400. Actually, if they are indexes, their sum must be 400, because there are 4 seasons, their averages are 100. Okay, based on 100, we computed and got 40.65, 68.13, 169.32 and so on. So how can we fix this? The easy way is we will compute ratio of each value to average again. Therefore, what is the average? 392.19 by 4. This is the average value. So let's see idea of the last step. Okay, the average is 392.19 by 4. This is the average. So you find ratio of each value to average. 40.65 divided by average, the percentage from 100. Actually this is equal to, mathematically, 40.65 multiplied by 400 over 392.19. Similarly, season 2 index 68.13 multiplied by 400 over 392.19. You get this. And season 3 169.32, you multiply by 400 over 392.19. So you multiply each index by 400 over 392.19. So this common factor is called adjusting factor. 400 divided by 392.19 is equal to 1.0199. So you multiply each of the indexes by this factor, then you get the last adjusted seasonal indexes. This is the final answer.